Following reaction occurs when sodium bicarbonate is heated. So you know this typical reaction. So sodium bicarbonate will give carbonate, CO2 and water, and this is how we remove primary hardness in water. Typically primary hardness is because of this bicarbonate. So this is how we remove. So you heat it. So you might have seen this in at home sometime. When hard water is heated in kettles, after some time there is a small white color layer that is deposited on the surface of the bottom part of the kettle. So that is because mainly of these carbonates. Okay, so that is how we remove. A sample of sodium bicarbonate was placed in an evacuated rigid container of 5 cubic centimeter, cubic decimeter. So I will try to draw as it is. So we have a vessel of 5 cubic decimeter, and there is this NaHCO3 sample solid, and it was heated. Okay, so at 328 degrees. So automatically there will be this equilibrium. Na2CO3 to NaCO2 gas plus H2O. Is this balanced? Yeah, they have given the balance equation. And after the equilibrium was reached, a small amount of sodium bicarbonate still remains. So no problem in that. The pressure of the container was found to be 10 to the power 6. So PT is given, that is 10 to the power 6 Pascal. And assume that the volume of the solid, so the remaining amount of this sodium carbonate that is going to be remain here. So they are telling neglect this volume. So what is the reason for that? Neglecting this volume means you can take this volume of these gases as the volume of this container, because these gases will be distributed throughout this container, right? So you can omit the volume of this solid. And they have given take RT as 5,000 joules, maybe, yeah, joule per mole at 328 degrees. Calculate the number of moles of H2O gas in the container when the equilibrium is reached at 328 degrees Celsius. Calculate Kp for the above equilibrium. Okay, so this is a solid, these two are gases, and calculate Kc as well. And there is another additional question. So first we will calculate the number of moles of H2O. So we need to calculate H2O gas moles and Kp and Kc. Okay. So we will discuss this very quickly, right? So when this reaction is happening and this reaction becomes equilibrium, right? You need to understand there is this. Let's say we don't know the number of moles of sodium bicarbonate that is used. So we will assume this as 1 mole for an example. So at equilibrium, you have to understand if the dissociation is like 2x for an example, let's say. So this the amount that will be remain at equilibrium is 1 minus 2x. So 2x amount is reacted. Why I took 2x? Because there is a stoichiometry 2 here, so it will be easy for me to balance the product side, right? Then at equilibrium, the product side, so 2x is reacting, which means x is going to form because the stoichiometry is 2:1. And here also the stoichiometry is 1. So x will be formed, which gives you the idea at equilibrium, the molar ratio NCO2 is to NH2O is 1:1. That's the idea, right? So same amount of CO2 gas and same amount of H2O gas is going to form at equilibrium. And this total pressure that is given here is exerted only by these two gases, because solid does not have vapor pressure. So they all have only solid pressure. So here this pressure is contributed from CO2 and H2O, and the amount that is formed here is same. Therefore, you can write the mole fraction x CO2 is equal to 0.5, and which is equal to x H2O. Therefore, PH2O is equal to x H2O times PT. This is according to You have to write according to Dalton's rule. Therefore, you can write XH2O is 0.5, PP is 10 to the power 6. So basically, 5 into 10 to the power 5. And this would be same for water, and as well as same for CO2. But in the question, they have asked only about water. They have not asked about in CO2. But the next question says, now this is done, to find Kp. So the Kp equation for this particular equilibrium, Kp is, what are the gases? So these two are gases. So partial pressure of CO2 gas times partial pressure of H2O gas over solid. No, so nothing is there. So Kp is just partial pressure of CO2 and partial pressure of H2. So here for this one, you need the partial pressure of water as well as partial pressure of CO2. So you can write PCO2 is equal to 5 into 10 to the power 5 Pascal as well. Because mole ratio is 1:1, we have already written in the previous question. So you don't have to write it again. So here this will be 5 into 10 to the power 5 Pascal times 5 into 10 to the power 5 Pascal. So it will be 25 into 10 to the power 10 Pascal square. So this is our Kp expression, the value of Kp. Then you need to find Kc. So what you can do here is, now you know the partial pressure of this. You know the RT value. So you can plug PV is equal to nRT. RT is known 5000. CO2O, I the H2O you don't know, so you take that as like an N value. Pressure V all known, so you can find number of moles. Then you can divide it by 5 decimeter to get the concentration, because in Kc expression you put the concentration, not the pressure, unlike Kp. So the Kc expression is concentration of CO2 gas times concentration of water gas. Okay, so to find CO2 concentration, you have to first find the number of moles, then divide it by the volume to get the concentration of both, because both will be same, because same amount of CO2 and H2O is. But you don't have to worry about that, because we have the typical expression, right? So Kp is equal to Kc RT delta N. So if you can remember, you can directly use this equation. So I recommend you to use this one. Don't go through this one because it will cost some amount of time. Okay, so essay paper, the main part is saving time. That's the idea, right? So you know Kp, you know RT is given 5000, and delta N is the products minus reactants. So you can see only two gases are formed, 1 and 1 is 2. So delta N is 2 minus, in the reactant side there are no gases, so 0. So delta N is 2. So you can use this expression to find Kc. Okay. So that's the simplest explanation that I can give to you. Right, so we have done this one and this one. Very simple, right? Then they say an extra amount of CO2 gas was added into the container described above at 328 degrees. Okay. What they have done, now initially this equilibrium is attained, then again they add separately some amount of CO2 gas. When the equilibrium is re-established, the partial pressure of CO2 gas was 4 times the partial pressure of water. Calculate the partial pressure of CO2 and water under this condition. You don't have to do much, because you know Kp, and you know that Kp is constant at constant temperature, right? Right. So what they have done, they have added some amount of CO2 at the same temperature, 328 degrees Celsius, and a new equilibrium is formed, right? So at this new equilibrium, what are the things that is not changed? Because the temperature here and the temperature here is same. So your Kp expression is not going to change. It will be 25 into 10 to the power 10 Pascal square, right? What is going to change here? When you add CO2, the CO2 concentration is increasing, but they have to maintain this Kp. So in order to maintain Kp at constant temperature, this equilibrium should shift towards the side where they maintain this Kp expression. So there will be a new equilibrium that is established. And they have given at this new equilibrium, the partial pressure of CO2 was 4 times the partial pressure of water. So if you take this partial pressure of H2O as Px, carbon dioxide will be 4Px. So that is the only thing that you can get from this description, right? Then they are telling find the partial pressure of H2O and CO2. So what you can see from this, straightforward, right? Because you have the Kp expression. So Kp is not going to change. This is not going to change. That is the main advantage. If this is not changing, PaCO2, PH2O. This is the expression, right? Times. So Kp is 25 into 10 to the power 10 Pascal squared. PCO2, you can put this in terms of Px. So this will be 4Px times Px. So finally, this is going to become Px squared. 4Px squared is equal to 25 into 10 to the power 10 Pascal squared. So you can get Px here. You can get the root of this, and this root will be 2, and this root will be 5. So 5 over 2 is 2.5. Root of this is 10 to the power 5. So Px will be equal to PH2O, and PCO2 will be 4 times 2.5 into 10 to the power 5 Pascal, which is 5 over 2, 2 to cancel means 10 to the power 6 Pascal. 10 into 10 to the power 5, which is 10 to the power 6 Pascal. Okay. So the critical point here is you have to remember, you change the concentration or either pressure or anything, you re-establish the system. If it is happening at the same temperature, your Kp is not going to change. That's the only idea that you can take from this question, right? They have tried to re-establish the equilibrium by adding a certain amount of CO2 here. Right, so we will go through this. Yeah, this is done now. So typically the part A is done, right? So we'll move on to part B here. So it's the same equation, but here it is reversible, and here we are dealing now with a irreversible reaction. So this might be more or less related to kinetics or either maybe thermodynamics. So we will discuss. So in order to determine the standard enthalpy change, delta H, so you need to determine this delta H here, okay? The following experiment consists of 2 steps, 1 and 2, was carried out at room temperature, so no problem in that. So 0.08 moles of NaHCl3 was added to 100 cubic centimeter of 0.1 mHCl, 1 mHCl acid solution in a beaker, okay? So here in the setup 1, we are adding 0.08 moles of NaHCO3 to 1 m 100 cubic centimeter. So we are using a beaker, right? Normally these experiments are carried out in calorimeters, right? So we don't use beakers, we use calorimeters, right? And the maximum temperature fall was found to be 5 degrees. So what is happened here? The temperature is fallen, right? Which gives the idea this reaction is endothermic because the system absorbs. So your enthalpy will be positive, right? Because temperature is fallen. So enthalpy delta H should be more or less positive, right? So This is the reaction that is taking place, NaHCO3 with HCl giving Na plus. This is the reaction that is going to happen. In the step 2, they have differentiated the number of moles of sodium carbonate here. So here this is 0.04 moles of sodium carbonate. So initially in step 1, it was sodium bicarbonate, but here it is sodium carbonate. So what is the reaction that is happening? That is the important part for us, right? So to the same solution, so 1m HCl 100 cubic centimeters, so the volumes are same, and the temperature rise was 3.5. So this gives the idea when the temperature is rise, which means this reaction is exothermic, and delta H now is going to be negative, right? And this is the reaction that is happening, and they have given some additional piece of information. The specific heat capacity at constant pressure and density, and the density of the solution is given. So density is density of water, which gives you the idea. If you use like 100 cubic centimeter, the mass is 100 cubic centimeter. That is what the density means, right? Assume that the changes in the volume and the density of the solution of the addition of the solid, okay, is negligible, so that is fine. Calculate the enthalpy change in kilojoule per mole of the reactions given in step 1 and step 2. So this question was a little bit different because we don't have any information of these formation enthalpies and all those things. But this question is very simple as O level, because here to find the amount of heat energy, okay, delta H, you can use mc delta theta. Okay, that is why they have given this specific heat capacity and the density, right? So for mass, you can use dV because density is 1 gram, volume is 100 cubic centimeter because we are avoiding the volume of these solids. So C is given 4 grams, and delta theta, remember for step 1, delta theta, you have to use +5. Don't forget. But this is for step 1, right? But for step 2, don't forget, you have to use delta theta as -3.5. Okay, then you have to find these two values, and this will be a positive value, then this two will be a negative value. So here when you solve this one, you will get an answer in kilojoule, but you have to find this in kilojoule per mole. So how do you do that? For that thing, you have given the amount of sodium bicarbonate that is used and sodium carbonate that is used. So the kilojoule amount that you find here, divide by 0.08 in the first step, then you will get this as in kilojoule per mole. In the second step, you have to divide this by 0.04 moles, right? So you can get these two as answers. It's straightforward, right? And the next thing is using the values that obtain in one above and a thermochemical cycle, calculate delta H of the reaction, right? So I will try to share the screen and explain this thing because it will be easy for me. Very quickly, yeah. So for step 1, the reaction is NaHCO3 solid that gives the reaction with HCl. That is going to give Na plus, Cl minus, all those things, H2O and CO2. This is step 1. And in the step 2, it was sodium carbonate, and 2HCl is going to give Na plus, Cl minus, H2O, and CO2. And you know, for this step 1 reaction, there was delta H which is positive in value, And here in this one, delta H is negative in value, and you know this value as well in kilojoule per mole. So you know these two, right? But we have to find the enthalpy of this reaction. What is that reaction? 2NaHCO3 giving sodium carbonate, H2O, and CO2. So what is the difference between these two? I'll stop the reaction. Okay. So what is we have to find this one, delta H of this one. Now tell me, what is the difference between these two reactions? Think about that. There is NaHCO3, HCl, Na plus Cl minus water compound. Na2CO3, HCl, water compound. So what is missing in this particular reaction? That's the thing that you have to understand. What is actually missing here from these two reactions? When you see this, you can understand the missing part here is this HCl. Okay. Then you can go furthermore. What is that? When NaHCO3 reacting with HCl, it gives this. When sodium carbonate reacting with HCl, it gives the same compounds, right? Same compounds. So you add HCl to this, you add HCl to this, you are going to get the same compound. So when you add HCl here to this side and even to this side, you can balance, because see here, if I add HCl here and HCl here, since they have used like 2:1 in the particular reaction, so you can think about balancing this. So I'm going to add 2 HCl here and 2 HCl here. Right? Now think, when these two reacts like in the same way here, what are your products? Well, it should be these, right? 2Na plus, because here the stoichiometry is 1:1, but here I use 2. So 2Na plus, 2Cl minus, 2 water, 2 CO2. So this is this reaction that I know these values are delta H positive. So this is positive. But here this is for 1 mole, but here this is for 2 moles. We use 2 HCl and 2 bicarbonate. And then what is the reaction between sodium carbonate and 2 HCl? That is the reaction that is present here. It gives 2 Na, 2 Cl, water, and this. In fact, we have to find 4 water. Yeah, this is correct. Yeah, that is correct. Then here you can put this one as an arrow as well. And this one, we know this is a negative value, because for this particular reaction, it is negative. But don't forget, this negativity and this positivity does not mean in the same reaction. These two are in different reactions. So in this thermochemical cycle, so this is negative and it is the same reaction that is going to form, because there is additional H and Cl here. That is why this is 2Cl here. The reaction is sodium carbonate and 2HCl. So the same reaction is happening here. And the only thing that you don't know here is delta H, right? So according to the Hess's law, so now according to the Hess's law, you can apply, right? So this is our reaction. So delta H for our reaction plus this negative value, plus this is the other way around. So you can put the plus minus this thing, or this should be equal to positive times 2. Clockwise arrows equal anti-clockwise arrows. That is the Hess's law. So this is clockwise, this is clockwise, this is anti-clockwise. So the anti-clockwise is equal to 2 clockwise processes, right? So you know this one, you know this one, and you can only find this delta H. Okay. So that is what they have asked in the question. So I will come to the question now. So you can use this thermochemical cycle to find this answer for this particular question. State the condition under which a heat change of a reaction is equal to its enthalpy. So normally we calculate this as the heat change, but at constant pressure, which is also given here in the description they have given here. See, so heat capacity on constant pressure. So basically, heat energy will be equal to enthalpy at constant pressure. So don't forget that ever. Okay, that is very important. Last question. Identify two sources of error in the above experiment. So I have told one error before in the beginning. So I told you here we have used beakers. For normally for this enthalpy related, thermochemical cycle related, this for thermodynamics, we don't use beakers, we use calorimeters, right? Which also contain some sort of regiforms around it to minimize the heat loss. So the first source of error is we have not used calorimeters. And the second error that can be is heat energy lost to the environment, right? So those are two errors that you can mention here. Okay.